welcome to this module 49 of the manufacturing process technology part 1 course. This is the concluding module for the welding, beyond which we will probably try do some problem solving to help you guys to do the exams well, which is due in the next week and next to next week respectively. So, let us just quick recap of what we did in the last lecture. We talked about contact resistance and various heat sources, and also talked about the resistance heating, where a contact bridge is established between the asperities from both the sheets which are participating in the weld, which results in the sort of formulation of paths where there would be localized heating, and because of the localized heating there is a high heat, high contact resistance driven heating, which kind of melts the liquid and then it solidifies and recrystallizes to form the joint sheets. So, today we are going to actually look into the process of again switching gears a little bit and looking into the process of the arc welding particularly, and how the metal transfer takes place from the electrode to the weld section. So, if we really look at the modes in which such metal transfer would happen, there are few facts which we need to understand before starting to do that. The depth of penetration and the stability of the weld pool, and also the amount of spatter loss depends to a large extent on the mode of the metal transfer from the consumable electrode onto the welding zone. So, various forces cause the transfer of metals into the weld pool. The mode of transfer depends on the intersection of these forces and governs the ability of welding in various positions. The major forces which take part in this process are that due to gravity, because obviously the drop which is emanating in the liquid state from the electrode would be pulled down or repelled down by the forces of gravity because of its weight. There is also a component of surface tension, because obviously you are formulating a liquid gas boundary, and there is bound to be a surface tension which withholds all the melt droplet on the tip of the electrode, and therefore, surface tension is a very, very important force. There is electromagnetic interaction, because it is going to be a high current transfer process. As you already know, there is a arc which is established, and the arc is nothing but a series of ions and electrons. So, there is some electrical activity which results in some kind of a ion current, and owing to this ion current there is going to be Lorentz forces because of the magnetic field which is created by motion of these charges, and therefore, there has to be some kind of electromagnetic interaction, and then hydrodynamic action of the plasma itself. So, plasma, depending on where it is created and where the ions are moving, would allow the droplet to move into a direction which is the path of least resistance. So, therefore, I am not talking about electrical resistance, I am talking about least mechanical resistance. So, therefore, all these different forces govern the mode in which the liquid metal emanates from the electrode and comes to the weld zone. So, the force of gravity may be retaining or a detaching force, obviously, because if you are doing overhead welding, the droplet would like to fall down, and if you are doing top down welding, it is an advantage, because the droplet which falls down actually goes into the weld zone. So, depending on whether the electrode is pointing upwards or downwards, you may either have a retaining force to the weld zone or a detaching force from the weld zone. Surface tension always tends to retain the liquid drop at the tip of the electrode. So, this force really depends on the radius of the electrode, the capillarity constant, and the density of the liquid metal. The electromagnetic force, Lorentz force, is set up due to the electromagnetic interaction of the electric current and its own magnetic field. So, that is another force which I think I had just described. Because of its own magnetic field, the current, the ion current across the electrode and the metal is going to give magnetic forces, and also the force acts in the direction of the current when the cross section of the conductor is increasing, and vice versa. So, the figure on the left explains how this force sort of accelerates the process of separation. You can see that there is going to be separation of a droplet which has started to separate out. So, you can think of the forces, the Lorentz forces, to be applying in this direction, obviously, because if you have a current in direction this or this, depending on primarily whether it is the ion current or the electron current, there are going to be magnetic fields associated with such currents, which emanate in a circular manner owing to the direction of the current. By using right hand grip rule, you can figure out the direction of these magnetic fields, and this magnetic field would have interaction, because obviously as the the magnetic field is in a perpendicular direction and the motion of the electrons is either towards this or towards this direction. So, in a perpendicular direction there will always be a sort of a force which allows the droplet to split. Okay. So, the hydrostatic pressure is created due to the magnetic force, and at high current density this pressure elongates the liquid drop and also adds to its stiffness. So, you can think of it that this section, formation of this section is a result of such forces which is always in perpendicular direction in both the directions, and you are trying to sort of make the liquid necked around this particular region. As a result, the liquid drop is projected along the line of the electrode independent of the gravity, even though the gravity would allow the drop to simply go down. This force, the presence of this force would try to pull along the droplet, and the plasma of the arc also causes the drop to be projected towards the workpiece. Obviously, there is going to be a formulation between the melt drop and the iron. So, there are many current paths which are created between the two, and there is a plasma in this particular zone. So, it is a kind of hydrodynamically focusing arrangement that the plasma offers, and this droplet which has been separated because of Lorentz forces and a combination of the surface tension and the gravity forces here is now coming into the path of the plasma and being hydrodynamically focused onto the workpiece. So, all these forces interact in a very complex manner and give rise to two broad classes of metal transfers, and we would like to call these either a free flight condition or a short circuiting condition. And as the name implies, it is obvious that in a free flight condition the droplet is now separated from the electrode, as you can see here. Okay. And there are various cases of this droplet separation. One is the projected case, another is the gravitational case, third is the repelled case, and I am going to describe these independently. Okay. So, this is the free flight mode, that means the droplet has separated from the electrode, and the other mode that is available is basically the short circuiting mode, where you are seeing that the droplet is still in between the electrode and the workpiece. So, this is the workpiece, this is the electrode, and it is sort of making a contact between the electrode and the workpiece, and this contact gives to a increase in the current, etc. And so, this is called a short circuit transfer. Okay. So, therefore, in one case the drop comes free in flight, another you have sort of a connection between the electrode and the workpiece momentary, and that is called a short circuit transfer of the metal. So, in the former, that means in the free flight condition, the liquid drop travels freely in the arc space, gets completely detached from the electrode before contacting the workpiece, and the free flight transfer may be seen in the figure above. Okay, here. So, projected case, when the electromagnetic forces, the jet of the plasma which creates some kind of a hydrostatic pressure, they are predominant in nature. So, there is a tendency of the droplet to sort of emanate or separate from the electrode and move in the direction of the plasma all the way to the welding zone. So, this is the projected transfer of the droplet. Instead of the fact that the droplet was having a gravitational force in this direction, the droplet travels in a slightly angular direction because of this different effects of electromagnetic and hydrostatic pressure created by the hydrodynamic focusing of the plasma. Okay. So, in the gravitational case, though, the force of gravity is outnumbering the other forces which are present, and the drop simply drops off, okay, in the vertical direction. And if the resulting force is such that it directs the drop away from the transfer zone. So, these are called the repelled kind of transfers. So, there may be a possibility that the combination of the surface tension force, the gravity force, and also the Lorentz forces may be enabled in a manner that the droplet separates and moves outside the zone of welding. So, effectively the metal transfer within the weldment is very low and it goes out, and this is called some kind of a, you can associate a defect with respect to this, because the welding is not proper because of such conditions, and it is called a repelled kind of metal transfer. Okay. So, a repelled kind of metal transfer may be important, particularly in overhead welding, where there is a tendency of the droplet to fly off the zone of welding, and it could result in some kind of a stiction because of this throwing away onto another part of the surface. Okay. So, that is how you categorize the free flight cases. In short circuit transfer, the liquid drop at the tip of the electrode gets in contact with the weld pool before getting detached from the electrode. Now, arc is momentarily short circuited. So, there is a huge amount of current which flows because of the short circuit. However, due to the surface tension and the electromagnetic forces, the drop is now pulled into the weld pool, separated, and the contact with the electrode is broken because of that. So, ultimately any short circuited transfer process is followed up with a free flight, because not a free flight exactly, but with a breakage of the connection which re-establishes the arc again, and then it can melt more material from the electrode in this process. So, this type of transfer, being independent of gravity, is good for overhead weld applications, you can say, and also I told you in the repelled case as well, there is going to be good application to the overhead welding applications. So, let us now look at the different heat flow aspects which can probably give us an idea of the microstructure. I would like to recall that in the casting problem, when defining the problem, etc., we did a lot of these studies, and related to the recrystallization and the grain boundary or the grain size, etc., there could be a predictable set of properties of the material because of the different heat flow rates. So, a study of heat flow characteristic in this case also is going to provide an estimate of the minimum heat input rate required to form a weld of given width, okay, and moreover a recognition of the major variables controlling the thermal cycle, that is the heating and cooling rate of the heat affected zone, etc., is essential for a successful fusion weld, because in fusion welding process the heat source particularly moves, it is like a lateral. So, basically when we are talking about joining two materials in a butt weld formulation, there is always a tendency of the the material to be laid out into the plane in this particular manner, and so therefore, the heat source typically has to move along the length of the weld, and therefore, analyzing such a problem with a moving heat source is to assume the source as a stationary and workpiece to move with the same velocity in the opposite direction. Okay. So, that is how all the analysis of the heat transfer would be done, and this essentially defines the limiting condition, which is the speed at which the weldment is being made or speed at which the welding process happens. So, two different types of heat sources can be considered. In most cases, the heat is liberated in a small zone which is identified as a point source, and the heat flow from the source is 3-dimensional. In a few cases, in a butt welding of relatively thin plates, the heat source is liberated along a line and the heat source is idealized as a line source. So, in such a situation, the heat flow is typically 2-dimensional, and we would like to just simply give you the heat transfer model without getting into the details here. I think I had done a fairly good amount of analysis in casting, but for the two different cases, like for example, the case of a 3-dimensional heat source, which is not really a line heat source, but a point heat source like this, and assuming that the workpiece moves at a velocity v with respect to this heat source, the Q, the rate of heat input in watts, is simply given by 5/4 pi W k theta m 2/5 plus V w by 4 alpha, okay, where W is the width of the weld in meters, k is the thermal conductivity of the work material, theta m is the melting point of the work material above the initial temperature, V is the welding speed in meter per second, and alpha is the thermal diffusivity of the work material, which is given by k by rho c. In the other case, that is when the source is treated in the case of thin plates, etc., when the source is not treated as a 3D anymore, but a 2D with a line source resulting from the weldment. So, in that case, the equation would be modified slightly, and Q is given now by 8 k theta m h 1/5 plus V w by 4 of alpha, where h is the additional plate thickness term which comes into picture, and other parameters remaining the same. Theta m is the melting point, k is the thermal conductivity of the work material, w is the width of the weld, and v is the velocity of the weldment, meaning thereby in this case the workpiece is moving with respect to this line source at a velocity v. Alpha is the thermal diffusivity. So, this is how you basically characterize the velocity of the weld. Let us actually try and do a problem example. So, how do you first find the Q or the rate of heat input? So, essentially if supposing C is the total fraction of the time during which the arc is on and transferring the power, and power is transferred as V I. The total power, that is the power in watts or kilowatts, whatever you may record, is C V I, where C is really the duration of the time for which the power is being delivered, and V I product is basically the power. As you all recall, power actually is in watts, joules per second, which had been also given as the rate of heat input. In this case, we really do not assume any other losses, and we assume all the power is being applied in order to melt the weld, because the power delivery is a huge power, and there are, although there are some chances of heat dissipation, but we are trying to sort of just consider that to be negligible in comparison to the actual melting and the application of the liquid metal to the weldment. So, in a butt welding process, for example, the arc power is calibrated to be 2.5 kVA, and the process is used to weld 2 steel plates, each of which has 3 millimeters thickness. We want to sort of go ahead and find out the maximum possible welding speed. We assume that the metal transfer is of short circuit type, and the arc is on for about 85% of the total time, and we have given some parameters like the alpha, which is the K by rho C term for the steel, is 1.2 10 to the power of minus 5 meter square per second, and we have also provided the thermal conductivity for steel, K steel, as 43.6 watts per meter degree Celsius, and the melting point of steel is about 1530 degrees Celsius, and the ambient temperature is assumed to be about 30 degrees Celsius. So, let us first calculate what is going to be the rate of heat input. So, the rate of heat input in this case is provided by CVI. C is 85%, so 0.85 times of voltage, which is 2.5 voltage current product, which is 2.5 into 10 to the power of 3 watts. You already have this as 2.5 kVA. So, this comes out to be about 2.12 10 to the power of 3 watts. That is how much power is being sent into the for the welding application. So, the minimum width of the weld that has to be maintained, the minimum width of the weld to be maintained is given as W equal to AB. So, if we go back and have a look at this weld here, the overall distance AB is this distance right about here, and this comes out to be equal to twice root 3 for obvious reasons, because this right here is 30 degrees and this is 3 mm. So, automatically it can be determined, this particular length can be determined as 2 root 3. So, this 2 root 3 becomes equal to 3.78 into 10 to the power of minus 3 meters, and also the theta m, which has been mentioned here, is equal to 1530 minus 30, the ambient room temperature, which is 1500 degrees Celsius. H is basically the height, which is in this particular case the thickness of the plate, about 3 mm. So, also given as 3 10 to the power of minus 3 meters. The butt welding process involving thin sheets of size 3 mm can lead us to approximate the heat source as a line source, the heat source as a line source, and so the equation Q equal to 5 by 4 pi w k theta m times of 2 by 5 plus V w by 4 alpha remains valid. So, Q becomes equal to by calculating Q, it becomes equal to 8 times of 43.6 times of 1500 times of 3 10 to the power of minus 3 times of 0.2 plus V w by 4 alpha, and Q exactly is CVI, which has been calculated earlier as 2.12 10 to the power of 3 watts. So, obviously, the 0.2 plus V w by 4 alpha becomes equal to 1.25, or V w by 4 alpha becomes equal to 1.05. I am sorry, 1.05. In other words, if I substitute the value of alpha here, the for a minimum width of twice root 3, the maximum velocity that can come out becomes equal to 0.0146 meters per second. Okay. So, this V for the minimum width W equal to 2 root 3, and for the value of alpha equal to K by rho C of the steel has been found out to be 0.0146 meters per second. So, in fusion welding, the other important heat flow variables are the cooling rate and the thermal cycle, of course. So, let us just look at individually the heat flow, other heat flow variables, like let us say the cooling rate and the thermal cycle. We can, by a simple mathematical analysis, come to some conclusions which suggest that the cooling rate increases with increasing the weld speed, and for a given weld speed the cooling rate decreases with decreasing the size of the weld pool. For example, in electroslag welding, for example, since the weld pool is large and the welding speed is very slow, the cooling rate is seen to be very low. On the other hand, in automatic tungsten inert gas stick welding processes, the process is operated with a very high speed, because there is an auto feed of the wire which comes out, and there is a relatively smaller weld pool, because this typically TIG is carried out with not very wide area welds, and this results in a very fast rate of cooling. Okay. So, the thermal cycle at any point in the medium is mainly governed by its distance from the heat source. So, obviously, with increasing distance from the source, the maximum temperature is lower and the temperature lags further behind the source. You can see the plot here. So, this gives us an overall distance as a function of distance from the heat source, the temperature versus time, and you can think of it that at a peak point of delivery of the power, the temperature increases, and it rises to the level of almost the melting point and then falls back, and you are basically increasing the distance from the heat source in this direction. So, the temperature slowly, the peak temperature slowly reduces because of that, with a minimum temperature at a distance far away from the heat source, okay, corresponding to which the melting is happening. So, this is how the heat flow characteristics can be plotted. So, let us also focus on the gas metal reaction, what happens. So, the absorption of gas in the weld pool from the arc or the flame, it plays an important role, okay, in the fusion welding process. That is possibly true because of the gas metal reaction which may take place in the weld pool, and chances of such reactions are enhanced by high temperature of the gas and the metal, because obviously both of them have temperature which can suffice for that threshold energy or peak energy beyond which the reaction can take place. So, there are two different types of reactions which happen. In one type, the gas may just get dissolved in the liquid metal. So, this is more like a physical phenomena, physical dissolution, which may lead to weld defects or certain holes, pinholes. In the second type, on the other hand, the gas and the liquid metals may react chemically to form a stable compound, and this is even more dangerous because the strength of the joint may fall down because of formulation of such chemical compounds. So, in such a case, the situation may considerably be different depending on the degree of solubility of the reaction product in the weld pool. As long as the reaction product is soluble, it does not prevent the formation of a weld pool. However, it may result in an embrittlement of the welded joint. An insoluble reaction product produces either surface scales or slags, and thus physically interferes with the formation of the weld pool. Sometimes this is used deliberately for making the weld impurity proof. So, the slag typically rises all the impurity matter which is available within the weld pool. So, in this case either the excess gas of the weld pool is prevented or a flux is used to dissolve and disperse the reaction products. So, when a gas gets dissolved in the weld pool, there is obviously no hindrance towards the formation of the weld pool. However, as the solubility decreases on cooling, degasification starts, and with suitable nuclei the bubbles may form. So, if these bubbles are trapped, then the quality of the weld becomes very, very poor. So, even otherwise the degasification may make the joint very porous, and this defect basically is very common in metal whose oxides are easily sort of reducible by hydrogen and can be avoided by adding a suitable deoxidant in the filler material which takes care of such oxides. So, the temperature of the another important gas metal reaction is the diffusion of the gas into the parent metal from the weld pool, and when the temperature of the thermal cycle is high, thus this diffusion process may be quite fast. The diffusion of hydrogen into the heat affected zone may again cause an embrittlement of the welded joint. So, that sort of brings us to the end of this lecture on welding. So, I would now like to present a little bit information about the cooling of fusion welds. So, typically there are many mechanisms through which cooling can be described, but the three principal mechanisms where there may be some effect on the overall weld strength or the joint strength, etc., are contraction, which is a result of the cooling process. Then there is residual stress which comes in the weld because of again cooling, and then there are metallurgical changes which will be generated onto the weld surface because of this cooling action. So, let us look at one by one the different processes. One is contraction. So, during freezing of the weld pool, there is a decrease in the volume which takes place. Okay. Moreover, the direction of freezing and thus the effect of the contraction depends on the type of the joint. So, you can see these figures right here for example, and you can see how the contraction is taking place. For example, in A, it shows solidification of a groove weld which is partially frozen and it is solidifying. So, here the solidification front moves simultaneously from bottom upwards, okay, and also from sides inwards. So, that is how the solidification front takes place, and therefore, when the complete thing is frozen down, there is some kind of a piping effect which would occur throughout the weld, as can be seen here, because there is no metal to be fed in this contraction or shrinkage which happens because of solidification. Okay, you can take care of this by just putting the or by changing the joint orientation. For example, let us say in figure B, we are talking about an inside corner joint where molten cold metal is near to the surface of the pool. Okay, thus the top of the weld pool freezes faster in this particular case, okay, and a long piping throughout the joint may occur because of this fast freezing. So, we were discussing about the cooling of fusion weld. So, metallurgical changes associated with such cooling processes in the zone where the liquid is present, which is also known as the zone within the melt boundary and outside the melt boundary, makes a lot of difference to the way that the grain growth, etc., takes place within the weldment. So, if you look at this particular weld right here in this region, you can see that there are two base plates which are being welded by a liquid metal, and there is something called a melt boundary which is being signified by this area, beyond which the metal that is available is in liquid form as solidifying, and there is a zone which is away from the melt boundary, but into the main parent blocks that are being welded together, and this is also known as the heat affected zone, okay, or HAZ of the particular weldment. So, there are a lot of changes which are due to heating and subsequent cooling of the weld, and the heat affected zones of the parent materials may develop some kind of a different grain orientation. In this particular case, you can see that there is a coarse grain at some instances, and when you go away from the melting zone, you are having finer and finer until there is a cold worked grain size which has already started to pick up, because the heat affected zone, as long as it finishes, after that you have simply cold rolled steel or something which you are joining. So, the grains are quite elongated in that particular region. Okay. So, the changes significantly, as I earlier mentioned, affect the weld quality. How? There are various factors on which these changes would depend. For example, if let us say the material that is being solidified here is a two phase material or a single phase material, they may have different properties on the total strength of the whole weldment. This probably influences the grain growth, the size of the grains, and so on and so forth. If it is a two phase material, it is still bigger a problem, because then there is a question of solid solubility versus liquid solubility of the material. You have already studied it in the material section, that a solid solution in a certain instance may not have the solid phase completely dissolvable within the liquid phase, and that is a function of temperature. So, if you keep on varying the temperature, you may find the solid phase precipitating out, one of the solid phases precipitating out, and there is only a small containment of the solid phase in the other phase which is being solidified. Okay. So, there may also be differences made because of prior heat treatment to the material and also prior cold working. In fact, these grain orientations that you are able to see in this zone is because of originally cold work material being joined to each other through this weldment process. So, let us consider this fusion welding now in little more details of two pieces of single phase material. So, this phase is single and this phase is single, and you have cold work to a desired grain dimension and you are trying to weld them together. So, obviously, the cold work regions would have more dislocations and they would have cylindric, sort of slender grains and probably squeezed grains, and it would actually demonstrate a lot more strength wise in comparison to this area which is actually the formulated grains. So, on fusion welding, however, a random grain growth will take place within the melt boundary, and that will lead to some kind of different sizes of the grains, as you can see in this particular region, growing from both the sides where heat transfer is taking place into the plates, okay, to the inside of the particular melt pool. Okay. And the problem comes actually in the heat affected zone, because there is, because of the, on one side it is almost liquid metal which is being solidified, there is some kind of a recrystallization of these grains which will start to happen, thereby resulting in some coarse grains, and then increasingly as you go away from the weldment and the temperature decreases, there is a fineness of the grain which comes in till and until it hits the actual cold work size of the grain which has happened in the original working steel. So, obviously, because of all these reasons, you may think of that the strength of the weldment may be different based on the grain orientation and size which comes in. In fact, this area is the hardest area, okay, and then because of this slender like growth of the grain, because of quick heat transfer processes, the weldment may be stronger, whereas this heat affected zone may be, because of the coarse nature of the grain, may not have that much strength in comparison to the weldment as well as the original cold worked metal. Okay. So, the case becomes a slightly more complicated when there are two phases that are being solidified, and one of the phases is precipitated out, because the solid solubility level of one phase in other may not be the same as the liquid solubility level. In this case, a two phase solid is being two phase material, two phase solid solution is being solidified as the weldment, and you can think of that there is a precipitation of the grain, and this grain would otherwise go to the heat affected zone, and there is a and also may get diffused into the overall the sheets which are being, the parent sheets which are being welded, and because of the effect of precipitation and the grain being inserted as an impediment to the dislocation process, there may be a strengthening action which may happen because of this precipitation followed by aging processes, okay, which takes place. So, a two phase welds are therefore very complex to be estimated in terms of strength, etc., in comparison to what a single phase would do. So, with this I think I would like to come to the other important welding process, which is like the solid liquid state joining, and as I had earlier said that there are three different processes here: brazing, soldering and adhesive bonding, which are grouped under the solid liquid state welding category, and the physical associated with each of these processes are essentially the same and differ mainly in the metallurgical aspects. And in these processes, the bulk material is not melted. Also, there is a molten filler material, usually whose melting temperature is lower in comparison to the parent metals, and it is used to provide the joint between the parent metals. So, in soldering, and brazing, the processes are carried out by allowing the molten filler material to flow into the gap between the parent bodies. So, all aspects including what is the wettability of the surfaces across which the metal would go and be a perfectly wetting material or be slightly dewetting kind of a material would actually even determine what is going to be the final weld strength. Obviously, the filler material has to have a melting point much lower than that of the parent bodies. I have already talked about this, and in case of brazing, the copper alloy that is being used here, it is again a two phase metallic solution, either it is copper zinc or copper silver that is being used, and the process, if this alloy is being used, is called brazing. A lot of automotive industries actually have certain steps, process steps, where certain areas are brazed particularly over and above the spot welding process, which is carried out in abundance in all the bodies of the automotives. And a similar process with lead and tin alloy can be done particularly on a slightly smaller scale, and it is also known as soldering. Okay. So, if the alloy changes from copper zinc, copper silver to lead tin alloy, the applications also change therein, and also the processes change, but the idea is that all these processes where the parent material is not melting and the filler material is the one which is molten, and still it provides the weldment or the joining between the parent materials, is categorized within the solid liquid state joining processes. So, most common source of heating for these kind of welding is again electrical resistance. Let us just look at the phase diagram of the different alloys that we have talked about. This is the lead tin alloy, which is used mostly for soldering processes, and this is the copper silver alloy, which is used for the brazing process. So, here we see that by varying the composition of the alloy, the flow temperature can be controlled within the range of 750 to 980 degrees in the case of copper silver alloy, and 160 to 300 degrees Celsius in the case of the lead silver alloy. Okay. So, therefore, if you vary the solid state composition by changing the percentage of silver as opposed to percentage of copper, or percentage of tin as opposed to percentage of lead, you may have different solidus liquidus points as can be visible in this particular phase diagram that has been given. So, first, the heating of the parent material is negligible to cause any change in their structure or properties, and second, these processes can join two materials which are otherwise insoluble in each other. So, that is an advantage of the solid phase welding process. So, to produce a perfect joint, obviously the entire gap between the parent bodies have to be filled up, and so this is achieved essentially through a capillary action process. The gaps otherwise are very small. Okay, and so the spreading and the wetting capacities of the filler liquid would play a predominant role in producing a satisfactory joint. So, the work of adhesion between a solid and liquid surface is governed by surface free energy according to this relation here. The work of adhesion is given by the surface free energy of the solid with respect to the vapor, that of the liquid with respect to the vapor, and then again solid with respect to the liquid with a minus sign on it. And basically it is expressed as joule per meter square, okay, and is numerically equal to the surface tension, that is Newton per meter, joule being Newton meter. Okay. And now from a liquid drop in contact with the solid surface, I think all of you have probably at some point of time done the Young's equation, which talks about the various surface energies balancing each other with a concept of contact angle. This is basically the liquid to vapor surface energy, this is the liquid to solid surface energy, as the name implies, this is liquid and this is the solid. So, it is an interfacial surface energy between the liquid and the solid, and similarly this is between liquid and vapor. So, you have gamma SV being equated to gamma SL plus gamma LV cos of alpha, and in fact the more is this contact angle alpha, the lesser wetting property the fluid will have on the particular surface, and it may not be a very conducive situation for creating a good weldment or for creating a good solder or a good brazed sample here. So, in fact the theory of capillary flow tells us two important facts, namely the liquid drop would rise to a greater height with a reduced gap. Okay, so, if the gap between the two parent materials are lesser, so you would expect the liquid to sort of go across a majority of the gap in a height wise manner, and the rate of rise is slower with a reduced gap. So, in fact the optimum gap maintained between the parts in such cases to be joined will be of the order of about 100 micron, about 0.1 mm, and now we will actually like to sort of review some of the important welding processes, and this is actually coming out of the discussion that I had online today on the video lecture, where some groups pointed out they needed a basic understanding of the processes. So, this is a in summary of it is like a summarized view of the different processes associated with the welding. So, we will talk about arc welding, for example. So, as you know that arc welding is created from a pool of molten metal, which is formed near an electrode tip, and in fact the electrode is melted to formulate this pool, and the electrode is moved along the joint. So, the molten weld pool solidifies, and that creates a weldment. In this particular illustration, you can see there is a electrode here which is being which is also creating a arc, and also this arc temperature is able to melt the material. You are also trying to create a another separate filler material. Sometimes the filler is actually coated on this particular electrode, and the direction of travel of the weld is shown in this particular direction towards the left, meaning thereby the plates that are being joined are placed parallelly, and the weldment is in the direction indicated by the direction of travel. There is also a AC or DC power source which is being shown, and an electrode holder, and there is a workpiece clamp which shows that how both the workpieces can be clamped together where the weldment is happening. There is also gas metal arc welding, where particularly this is a component which is used in automated processes or in industry where welding has to be done at a faster rate. Here you are basically feeding from a spool a wire, and this wire goes into a gun through which it comes out at a certain velocity, and it uses a consumable bare metal wire as an electrode. So, basically the wire comes out and gets molted, and that is what the filler material comprises of. It is being shielded by flooding with a sort of a gas around the arc, and as the wire is fed continuously and automatically from the spool through the welding gun, the welding process automatically happens. In this case, I think I had earlier illustrated that a drooping power source is not desirable, because it may be a possibility that for a certain type of arc with a certain arc length characteristics, voltage versus length characteristics, the arc may be blown off. Okay. So, shielding gases that are normally used are argon, helium for aluminum welding particularly, and for CO2 for steel welding. So, this is how you carry out the gas metal arc welding process. We also have a shielded metal arc welding process which uses a consumable electrode which consists of a filler material, actually a rod coated with chemicals that would provide both the flux and the shielding effect. Sometimes it is also known as stick welding. You can see here, for example, the electrode is getting extinguished, so it also produces the flux, also produces the shielding environment, and also produces the material which actually melts and acts as a filler. We also have a submerged arc welding process which uses continuous consumable bare wire electrode, as can be seen in this particular schematic here, with an arc shielding by a cover of a granular flux. This is the flux that is being dropped from a hopper which is ahead of the electrode, placed ahead of the electrode, and is used to flood the area in which welding is continued. The electrode wire is fed automatically from a coil, and a flux is introduced into the joint slightly ahead of the arc by gravity from the hopper, and it completely submerges the arc operation, prevents any kind of spatters or radiations or even in a way oxidation of the material which is being melted, and joins the surfaces together. We have some other form of welding here. For example, this shows a gas tungsten arc welding process which is carried out at an extremely high temperature. The melting point of temperature is about 3410 degrees Celsius, uses a non-consumable tungsten electrode with an inert gas for arc shielding, and you can apply these to mostly aluminum and stainless steels for welding them with this kind of a consumable non-consumable tungsten electrode. You can basically use with or without a filler material, and this process is when a filler material is used, is added to the weld pool from the separate rod or weir which you place somewhere nearby the electrode tip or the heat source. Then there is a process called plasma arc welding, which is a special form of the gas tungsten arc welding process, and it is basically with the deployment of a constricted plasma arc that you do welding on a surface. For example, you have a tungsten electrode which is contained in a nozzle, as you can see here in this particular cartoon, and it focuses a high velocity stream of inert gas argon in the arc region, as can be seen by this schematic here of shielded gas, and it is creates intensely hot plasma because of the breakdown of this medium and the potential difference between the tungsten electrode and the workpiece, which is otherwise grounded. Temperatures as high as about 28,000 degrees Celsius can reach in this kind of plasma arc welding process, and you can produce a plasma jet of very small diameter, so that the power density increases and rises, and a very high surface energy density can be obtained using this kind of arc welding processes. We also have some other form of welding like resistance welding. This is also known as spot welding, which is majority in a very major way used in all the automotive industries for all sheet joining operations. So here you can see here there are two electrodes which have a high current between them, as also pressure. So there is a solid state welding as well as some kind of a nugget formation at the sheet to sheet interface, where there is joining by virtue of a fusion welding process at the interface between the sheets. Okay, so it's a combination of that fusion welding along with a pressure which can sort of accomplish the coalescence process of the nugget, and that results in a hard zone in between both the sheets to join them. You can use this resistance welding method in a seam. So you can see here, for example, these are two sheet metal parts which are actually joined by a pair of rotating wheel electrodes, which produces a series of overlapping spot welds. Therefore, it is very, very important that these kind of processes be used for systems which will allow no leakage or very less leakage tolerances, particularly gasoline tanks, automotive mufflers. So you can produce airtight joints, almost airtight joints, with this kind of resistance seam welding method. We also have some welding processes using projection welding. So you can see here, for example, there are these two projections along which the resistance welding process happens. So it basically achieves coalescence at one or more small contact points on the part. The contact points can be determined by the design at the phase where you really need to illustrate the joint strength and how the two parts are being joined to each other. There is a roll welding process where it's completely either you have, it's primarily pressure driven. So pressure is sufficient to cause coalescence, which is applied by the two rolls between which the two sheets which are to be welded are fed in. You can do this process with or without external heat. So the variation of forge welding or cold welding depends on whether the heating of the work parts is done prior to the process. So in case it is cold welded, there is no heating. If there is a forge welding, there is some preheating action for this process to occur, and so you can have both hot rolled and cold rolled welds between sheets using this method. This is again another very interesting method of thermite welding. So we use this Fe2O3 and Al mixture, which is otherwise known as thermite, and there is a process through which the oxygen gets transferred onto the aluminum, and the reaction yields pure liquid iron and Al2O3. Slag here is used for lifting off this Al2O3 on the surface. So you have a formulation of liquid iron here which can be poured into the mold to have casting processes realized. Okay, so that's how you do thermite welding processes. You can also have explosive welding, where you can see here there is a coat of explosive between on the top layer of one of the sheets, which is placed in some clearance gap with respect to the sheet in which you want to weld this, and then there is a sudden area which is exploded, which thereby results in momentum and bending of the sheet, so that there is a pressure based welding that formulates, and so this is actually again another case of solid state welding. It formulates on the surface, and so that's how you do explosive welding. You can have also friction welding phenomena. I think there were some questions raised by some students here about this particular process, both the friction welding and friction stir welding. So here you can see the process starts with mostly on rotating parts where there are no contacts. So there are two rotating parts like this. The parts are brought into contact to generate friction heat between them, and suddenly the rotation is stopped and there is an application of an axial pressure, so that there is a nugget formulation here. So this is also a sort of a solid state welding, and here I would like to just illustrate one point. Please remember, in one of the modules earlier I had mentioned that when you are bringing two layers atomically close to each other, so that the gap between the layers is of the order of only maybe one lattice spacing, the amount of ultimate yield strength which goes and this kind of a orientation is much higher than the case where there is a crack which is propagated and there are several lattice spacings, maybe let us say 10 or more lattice spacings which are involved. Okay. So, in this particular case the failure that would happen between the sheet metal would depend on either the failure across the joint or failure of the material. So, as in the material there is a crack propagation mechanism which is responsible for failure, this would happen at a much lower ultimate shear strength yield strength in comparison to the yield strength of the joint itself. So, the material would fail before the joint. So, all the principles of solid based welding are based on this fact that you bring it so close to each other, so that it is almost one lattice spacing apart, and so the crack formation process which otherwise is a failure mechanism in the parent material would be done at a lower value of ultimate yield strength in comparison to the joint yielding as such. So, that you must remember is the basic premise behind all the solid state welding processes, and friction welding is also a solid state welding process. So, we have used this for many, so this kind of welding can be used particularly for circular parts like shaft or tubular parts, industries like automotives, aircrafts, farm equipments, petroleum and natural gas industries use this kind of applications. And you should ensure that at least one of the parts must be rotational in this particular process, and then the facing of the proper facing between the two parts has to be done a priori, because if there are flashes which are there, the welding may not happen to the extent that it is needed. So, it has to be perfectly almost sort of atomically flat for both the surfaces to have a weld strength which is more than the failure mechanisms of the material. We also have the friction stir welding process, and I think that somebody mentioned here, you can see. So, there is a shoulder which creates friction heat and welding pressure by rotation, and this rotation actually creates, these are the two plates, plate 1 and plate 2 to be joined here, and this shoulder is actually being rotated. Okay. So, there is a sufficient downward pressure that you basically give to this shoulder and then start rotating it, so that along the bay in which the shoulder kind of rotates, there is some kind of a solid state welding which is taking place here. Okay. The material really does not melt in this area, but there is some kind, because of friction and because of pulls and the pulling forces which are generated between both the materials, there is a overlap between the materials, and that creates a weldment as such between both the sheets. So, the advantages of such processes are that it has a good mechanical property of the welded joint. It avoids toxic fumes, because obviously if we were to melt and formulate a melt pool, there would be an additional problem of vapors and fumes coming out of the material. There it prevents any kind of warping and shielding issues. Also, there is very little distortion or shrinkage, there is no heat affected zone or nothing which causes, because obviously this is also a sort of a cold worked region, you can say, and so there is obviously a parity between the grain sizes of the welded zone and the parent material. So, there is a good weld appearance in general, and so therefore, this is a very widely used process in many industrial applications and does not need any filler material. So, the only disadvantage that the friction welding process, the stir welding process would have is that you have to have a place where you have to remove this shoulder from the basic material, and it creates an exit hole in that manner, and that is the only disadvantage that this friction stir welding process would actually have. And there is also, because you have to hold these pieces together at a high force, obviously there is some pressure and friction being transferred by the shoulder onto these blocks. Heavy duty clamping needs to be engaged in order to fix the parent material, so that such a pressure and such a frictional force can be withheld by the two plates. They cannot move while this frictional force is happening between the two materials, and that is how you do friction stir welding. The other important process is ultrasonic welding, USW. So, two components are held together and oscillatory shear stresses of ultrasonic frequencies are applied to the interface, which again causes some kind of coalescence between the materials here. So, this is the sonotrode tip which is vibrating through this ultrasonic transducer at a very high frequency, and these are typically the parts which are being welded together, and because of this high ultrasonic component you can see the vibratory motion here. For example, the sonic tip is vibrating in this particular direction. So, one of the plates are vibrating with respect to the fixed plate here. So, there is some kind of a shear between the both the plates which are happening because of this vibratory motion, oscillatory motion, and so this shear is able to create a solid state welding by making the surfaces go to the level of asperities and go close enough, so that it develops a good weld strength. Okay, so, this is actually a very useful process, particularly for the microelectronics industry also, because the temperatures that are used here are typically much below the melting point of the parent material, and it is particularly a very accurate process of working, because it does not really need ultrasonic transducers typically have very small magnitude of oscillation, and so there is not much amount of deformation which is needed in the tip as such, or the sonotrode tip, as you can see here, for causing a good weld to happen. So, this in general is a overview of all the different welding processes that I could think of, and what I will also like to apprise everybody is that the portion that has been done today is only a reference portion. It will probably not be included in the final examination, but you can see it for your reference and for your future preparation. Also, there were certain questions which were raised today which I tried to answer, and in due diligence with that, what we have also done is that we have uploaded a sort of model answers to some of those questions with the blog, and so you will get this available pretty much within tomorrow morning. So, I would like to thank all of you for being a wonderful part of this course, and I would also like to encourage you to sort of take the next course, which would be the Process Technology 2, being offered in the month of June and July. So, with that, I will like to take leave from all of you, wish you all the best in your examinations. Thank you so much.